This is section 7.2, graphs of polar equations. And in this section, we want to explore how to take an equation given in polar form, something that we don't know anything about, and plug in values to try to sketch the graph, to get a sense of what the graph looks like. Just like if we had a function we didn't know, that we didn't know the graph of, we might plug in some x values, see what y values go with them, what y values come out, and plot some points to get a sense of what the graph looks like. So let's see what that looks like in a polar situation. For example, starting here with being asked to graph r equals 3 cosine theta by plotting points. Now I want to use this table here to fill up some theta values, some convenient values, right? You've got your special angles in the first quadrant here, special angles in the fourth quadrant here, represented as negatives or just as positives. Right? Those are these guys in the fourth quadrant. And we're choosing these just because they're convenient values, but we want to plug these theta into this equation and see what r values come out. So let's see if we can do this. Let's start out with, if we have theta equals 0, that first column there, that gives me r is 3. Cosine of, instead of theta, I'll put theta equals 0. And that equals 3 because cosine of 0 is 1. So we get 3 here. Well, that just means when the angle is 0 with the x-axis, so right here's my x-axis, here's my y-axis. When the angle is 0, we're actually still on the x-axis. And it says when that angle is 0, we need to go 3 units. 1, 2, 3 units out from the origin in that direction. So we know this point I just plotted is on the graph of r equals 3 cosine theta. So let's plug in some more. Let's plug in r equals 3 times cosine of pi 6th. That's our next column. Theta is pi 6th going into this equation. Cosine of pi 6 is root 3 over 2, so this turns into 3 root 3 over 2, which when I compute it, I get this is roughly 2.6. So it says when we're at this angle, pi 6th, our distance from the origin is a little bit less. It's only a little more than 2.5, 2.6, right around here. So let me make that little mark. Maybe here. That's our next point. Notice that lies on the pi 6th ray. And I'll just go through here and fill these up really quick. When I plug in pi 4ths, I get 3 root 2 over 2, which, let me calculate briefly real quick, is square root of 2. I get that's roughly 2.1. So that's saying when we're at an angle of pi 4ths, we're even smaller in our radius than we were before. We're at 2.1, just past a radius of 2. And I'll fill those in here. And this is 2.1 roughly. Let's go through some more and then I'll plot them all at the end. At pi 3rds, it looks like I get 3/2, which is 1.5. Let's go and plot that one real quick. Oops, let me write that. It's actually exactly 1/2, but I'll leave that with my other decimal expressions. Plug in pi halves, it looks like I get r is 3 times cosine of pi halves. Cosine of pi halves is 0. So we're getting r is 0. When we're at this direction, the vertical direction, pi halves, we have r is 0. We don't leave the origin. We're actually at the origin right there. So mark that dot there. Let's get these down here. And then we can go through the opposite, but notice we remember that cosine destroys negatives. So if I plug in cosine of negative pi 6 into this, that cosine sees the same thing as positive pi 6. So I can actually read off what these negative values will get me just by looking at what the positive versions gave me. Looks like negative pi 6 would give me the same thing as positive pi 6, which is 2.6. Negative pi fourths, same as positive pi fourths. Negative pi thirds, same as positive pi thirds. And negative pi halves, same as pi halves, gives me 0. So let's see what happens when we plot these points. Well, at negative pi sixth, that's downward pi 6 from the origin, that's this guy. Our distance, downward from the x-axis, I should say. Our distance out in the direction of this ray should only be roughly 2.6 again. So same distance as this guy above it. So that distance from the origin to here is roughly 2.6. Then if we go down to negative pi fourths, we get 2.1, so a little closer, just over the radius of 2. Right, that looks kind of like this point did up here. And then you can kind of see what's going on. You're going to get this last point over here at 1.5 for your R value. Right, 1.5 for your R value when you're at negative pi thirds angle. And again, 0 when we get to negative pi halves. So when we're at the negative pi halves angle along the negative y-axis there, in that direction we get R0. We just mark the point of the origin. We're going 0 distance from the origin. And hopefully we can see what we have here is really just it appears to be just a circle. And if I was trying to figure out the center, well, this edge of the circle is at 0, the left edge is at 0, the right edge is at 3. I would think halfway in between there, 3 halves. Comma 0. That's probably your center of your circle. So let's see if we can confirm. We saw something like this in the last video, but let's see if we can confirm what we're thinking here. Let's see about this. Computer's frozen up a little bit here. Let's see what we can do. So let's see if we can confirm that this circle that we drew really does make sense for our equation. Well, if you remember in the last, there we go. In the last video, we saw how to convert something like r equals 3 cosine theta into an xy equation, a rectangular equation, so we could see what it looks like in more familiar territory. The xy expression is much more familiar to us. We saw the key here is multiply both sides by an extra copy of r. Then r squared over here, that's x squared plus y squared. R cosine theta, that's x. So we said, once you have it in this form, you can complete the square on both sides. Add half of this linear coefficient squared. Which is 9/4. And then we can write this as a perfect square on this side. To really view this as a shifted version of the standard circle, x squared plus y squared equals radius squared. Right? This is just a shifted version of that circle. Instead of having a center at the origin, it's got a center at the x has been shifted, so its center is at it looks like 3/2, comma 0, according to our equation. And the radius should be the square root of 9/4, which is 3/2. And that makes perfect sense with our picture. This is a circle shifted over 3/2 and having a radius 3/2, 1.5. All right, so this is what it means to plug in values to graph a polar equation. Plug in some convenient angles theta, plot the r values, the distance from the origin you should travel to hit your graph in each of those theta directions, those rays outward from the origin. And so we did mention this last time, but I do want to see it here. Oh no, I've caused another problem. Fixed it, okay. So the last thing I want us to notice is just what we saw here and in the last video. that something like r times a constant, r equals a constant times sine or cosine of theta, so either of these two equations down here, actually produces a shifted circle. And it's shifted by an amount equal to the radius. So for example, here it was shifted to 3/2, but the radius was 3/2 in our example. Whatever that a value is, that is really half of that is how far is what you're shifted by. Right? We had a 3 there in our case, and we shifted by 3 divided by 2. But so that's always going to be true. I gotta quit messing that up. Sorry. Right, so that's always true. What we also want to notice is that the equation r equals a constant just gives us a circle of radius equal to that constant. Right? This is just saying the radius, the distance from the origin, is always a fixed value. That's the definition of a circle of that fixed value's radius. Okay, so just a couple other things I want to look at here. Let's see if I can get this to snap out of it. Let's see what I can do. If I was asked to, yeah, that's better. If I was asked to plot an equation like r equals 2 by plotting points. Just notice that any theta value I enter, convenient ones or otherwise, oops, skip by fourths. Right, any theta value I think of, if I tried to plug this into here, all it would tell me is r is still 2. This equation for r is independent of the theta value. Right. So sketch r equals 2 by plotting points. So that would mean if I was actually going to try to sketch this thing, then at all of these angles, no matter what angle I look at, really any angle, I get the same distance from the origin at all of them. When I plug in theta equals 0, I get r is 2. So I get r is 2 here. When theta is pi 6, I get the same r is 2. So I get that same distance to the origin, 2. Pi fourths, same thing. Distance 2. Pi thirds, same thing. Distance 2 to the origin. Pi halves, same thing. Right? At every angle we go around, we want to mark that same distance of 2 from the origin. And very clearly, if we do that at every single angle, we do get this circle of radius 2. So if we did the same thing with sketching, maybe for a constant angle, maybe 3 pi fourths, I don't know, by plotting points. What would happen here? Well, if we did it in this case, now we're going to take it in the opposite direction. We're going to say no matter what r value, no matter what distance from the origin we specify, that plugging in here would tell me the theta value, the angle that goes with it, is always 3 pi over 4. So, for example, I could just plug in some r values. 0, plus or minus 1, plus or minus 2, plus or minus 3. If I plot what these give me, then notice the angle 3 pi over 4 is something that we're always having to adhere to. We have to stay at that angle. And that angle is this guy, right? That's the angle. That's 3 pi over 4. Well, this is the equation of the graph I'm trying to describe. So if I start plugging in some values like r equals 0, then along this direction we should go 0 units, right? Because this guy is not changing, not affected by my r value at all. R equals 0, I'm still in this direction of 3 pi fourths. I just go 0 distance from the origin in that direction. Well, if r is positive 1, it just means I go 1 unit in that direction. If it's positive 2, I go 2 units in that direction. Positive 3, I go 3 units in that direction. I could do the negatives as well. -1 means I go not in this direction, but just opposite that direction. Something like that direction. So go -1 units in that direction. -2 in the direction. -3 in the direction. We see that what we're getting is just this line of points. So that tells us more than what these facts up here explained about circles in polar. It tells us theta equals a constant is an equation of a straight line through the origin. Oops, a straight line. Okay, so that's really it for this section. We just wanted to see a little bit about polar equations and graphing by plotting. Circles are the big ones we want you to recognize just from seeing the equation. R equals a constant times sine theta, or a constant times cosine theta. All of those we can graph very quick and easy. I also think it's important to know that theta equals a constant gives you a straight line through the origin. But you can get these by plugging in points, or like we saw here with this argument down low here, we can get these circle equations through other considerations, doing some algebra. Okay, that's it for this video. Stay tuned for section 7.3.